Okay, so you guys have learned a little bit about the relationships between frequency and other aspects of the wave by playing with the simulation, and now let's make it a little more official with some equations. So frequency with speed has a direct relationship. Meaning if we increase the speed, we increase the frequency. Assuming that other things are staying the same. Frequency to wavelength has an indirect or inverse relationship, meaning if we increase the wavelength, we will decrease the frequency. And this was just based on the setup that happened to work the best for the simulation, but it's not necessarily that the speed and the wavelength are determined by something and then the frequency happens as a result of that. It could be kind of the other way around, where there's a frequency and a speed and the wavelength is the result of those two things. But these three quantities are all kind of in a relationship together. So let's first use these relationships to try to guess what the equation would be. And since we have them related to frequency, it would be F equals. Speed has a direct relationship, so that means it would be on the top. And wavelength has an inverse relationship, which means that it would be on the bottom. So hopefully this equation makes sense as kind of a conclusion from the work that you already did. But because dividing things is kind of annoying and it's easier to multiply them, the way that this equation usually gets written is if we were to multiply both sides by the wavelength lambda, we would get V equals F lambda. And this is the way that it is written on the reference table. So V equals the wave speed. And it's important to realize that this is not necessarily the speed of the individual particles that the wave is moving through. In the simulation that you did, there was those little green squares that move up and down. So those at any given time might have a different speed moving up and down, but that's not the speed that we're talking about. We're talking about if you were to follow this high point with your finger as it moves across the screen in the direction of the actual wave itself. So it's not the individual particles of the material, the medium. We're not talking about their speed, we're talking about the speed of the pattern as it moves. F, and this is usually in meters per second. F is the frequency. Its unit is hertz, which you might remember is per second, or 1 over seconds. And lambda is the wavelength, and it has units of meters. So let's do some examples. The first one will hopefully give you more of an intuitive understanding of this equation. So a wave is moving at 1 meter per second and the wavelength is 5 meters. So I'm going to draw a little person here, and then I'll draw kind of a nice big long wave. So if the wavelength is 5 meters from here to here, we want to think about how long will it take for this entire wave to move past this person who's standing here. So it's 5 meters wide, and it's moving at 1 meter per second. So that means that this part of the wave, 1 second later, will be 1/5 of the way over. And then after 2 seconds, it would be here. After 3 seconds, it would be here, 4, and 5. So it would take 5 seconds for this part of the wave to get to here, because it's moving at 1 meter per second, and this is a distance of 5 meters. So it would take, each second it would move 1 meter forwards. It would take 5 seconds. So it takes 5 seconds for one whole wave to go by. So that means that the period would be 5 seconds. That means that the frequency would be 1/5 seconds, which would be 0.2 hertz. So if we think about what math we just did, we took the wavelength, or to find the frequency, we basically had to take the speed and divide it by the wavelength, which is kind of this relationship that we started with. It kind of makes intuitive sense that the period would be like how long it takes for the entire wave to pass, and then from that we can get the frequency. So hopefully it sort of makes intuitive sense and you picture this happening. And this does also work out from the math perspective. V equals F lambda, 1 meter per second equals 0.2 hertz times 5 meters. This does actually work out to be meters per second, and 0.2 times 5 would be 1. Okay. Now let's also look at a similar example where we'll actually try to picture a person standing there. The wave is moving at 2 meters per second, and the wavelength is 0.5 meters. So we have a much smaller wave going on here. From here to here is 0.5 meters, one cycle, meaning from a top to a top is 0.5 meters. And in 1 second, it moves 2 meters. So here's half a meter, here's half a meter, here's half a meter, here's half a meter. So this together is 4 waves equals 2 meters, since each wave is half a meter. And this goes by in 1 second, because this distance of 2 meters worth is going to go by in 1 second, since it's moving at 2 meters per second. So we can kind of tell that the frequency needs to equal 4 hertz, because if we take those 2 meters per second, that gets divided into 4 waves, since each wave is half a meter, and that's how much is going by every second. So again, we're kind of taking this speed and dividing it by the wavelength to figure out how fast is each wave going by. Or we can do it in the formula. So if we hadn't already figured out that the frequency should be 4 hertz, we could write 2 meters per second equals the frequency times the wavelength is 0.5 meters. Divide both sides by 0.5. Sorry, 0.5. On this side, the meter units cancel out and we get 4, and the units are per second, but that's the same thing as hertz, equals the frequency. So either way you think about it, sort of drawing yourself a visual picture or using the formula, it should kind of make sense that these things go together. Sometimes the numbers get a little bit more difficult to be able to just sort of draw the picture if there's a really large number of waves, or if there's a really long wavelength, then it's a little harder to picture, like on the scale of being a person watching the wave go by, but the relationships are still the same. And one of the examples that you'll see a lot of is light waves. What's convenient about light waves is that the speed is always the same. The speed of light is 3.0 times 10 to the 8th meters per second. I think it might have a couple more digits on the reference table. It might be 2.99, but for this example, we'll just do 3.0 times 10 to the 8th meters per second, which is very, very fast. It's like 300 million meters per second, so super fast, way faster than you can sort of picture in your own head. But what this means is that you should expect that a really big number of waves is going to go by every second, because they're moving so fast. If you were to try to count how many waves just went by, it should be a really big number. So let's try to figure out what the frequency is of a light wave whose wavelength is 500 nanometers. So we're going to try to use V equals F lambda. V is also the special letter C, because it's this, which is what's used for the speed of light. And it's 3.0 times 10 to the 8th meters per second. F, we don't know. And lambda is 500 nanometers. Let's try to convert this to our standard units. So on the reference table, nano means -9, 10 to the -9th. So 1 nanometer is 10 to the -9th meters. So we can write 500 times 10 to the -9th, or we can move the decimal place over a couple times and get 5 times 10 to the -7th meters. So let's plug this in. V is 3.0 times 10 to the 8th meters per second equals F times 5 times 10 to the -7th. There we go. Divide both sides by the wavelength here. And remember, the answer should be in hertz. This would be 0.6 times 10 to the 15th. So I think we will get 6.0 times 10 to the 14th hertz as the frequency. But I did do that in my head. I don't have a calculator on me. So you might want to double check that. But I think it works out, yeah. So the light waves are both really small and moving super fast, which means that the number of light waves that go by in a second is a really huge number of light waves. When we're talking about light or other electromagnetic waves like radio waves or microwaves or ultraviolet waves or X-rays, these are all different examples of the same type of wave, and the only thing that's different about them is their wavelength or their frequency. We'll talk a lot more about that in like a couple of weeks, but one thing that tends to be common with electromagnetic waves is that they're just referred to by either their wavelength or their frequency, since you can always use the speed of light to figure out the other one of those two things. So if you know the wavelength of a light wave, you can use that to figure out the frequency and vice versa. So you don't necessarily need to have both of those numbers given to you, because you can always use the speed of light, that's always the same number, to find the whichever one is missing. Okay, hope this makes sense. Try the examples that are going to be set up for this, and let me know if you have any questions. Talk to you soon. Bye.